Download this code from codegive.com, link in the description below. Don't make this common error, premature optimization. Premature optimization, as famously stated by Donald Knuth, is the root of all evil, or at least most evil, in programming. This doesn't mean optimization is bad, it means optimizing too early in the development process, before you have a clear picture of where the bottlenecks are and how your code will be used, is often detrimental. This tutorial will delve deep into premature optimization, covering its pitfalls, identifying scenarios where it's tempting, offering alternatives, and showcasing practical code examples in Python, but the principles apply across languages. Why premature optimization is problematic. Premature optimization leads to several negative consequences. 1. Wasted time and effort. You spend valuable time optimizing code that might not even be performance critical. You're essentially solving a problem that doesn't exist yet. Development time is a precious resource, focus on features and correctness first. 2. Increased complexity and reduced readability. Optimized code often sacrifices clarity for performance. You might introduce intricate algorithms, obscure data structures, or convoluted logic, making the code harder to understand, maintain, and debug. Future developers, including your future self, will struggle to work with it. 3. Incorrect assumptions. You might base your optimizations on assumptions about how the code will be used or which parts will be the slowest. These assumptions could be wrong. Real-world usage patterns can be unpredictable, and profiling reveals surprising bottlenecks. 4. Increased risk of bugs. Complex, highly optimized code is more prone to errors. The intricate logic increases the chance of introducing bugs that are difficult to track down. 5. Hindered iteration and experimentation. Overly optimized code can make it harder to experiment with different approaches or add new features. You're less likely to refactor or change code that's been meticulously optimized because of the perceived risk of breaking its performance. 6. Negligible performance gains. Often, the optimizations you make early on provide minimal performance improvements in the overall application. The real bottlenecks often lie elsewhere. The golden rule: make it work, make it right, make it fast. This is a mantra commonly attributed to Kent Beck, and it encapsulates the right approach to software development and optimization. Let's break it down. Make it work. Focus first on getting the core functionality implemented and working correctly. Write clear, simple code that fulfills the requirements. Don't worry about speed at this stage. Make it right. Ensure the code is robust, well documented, and adheres to coding standards. Write unit tests to verify its correctness. Refactor the code to improve its structure, readability, and maintainability. Make it fast. Only after the code is working correctly and is well structured should you start thinking about optimization. This is where profiling tools come in handy to identify the actual performance bottlenecks. Scenarios where premature optimization is tempting. Let's look at some common scenarios where developers are tempted to prematurely optimize and how to avoid the trap. Loops and iteration. This loop is going to run millions of times. I need to make it as efficient as possible. Why it's tempting. Loops are often perceived as performance hotspots. The problem. You haven't measured the actual execution time of the loop. The loop might not be executed as frequently as you think, or the operations inside the loop might be inherently slow, regardless of your optimizations. Better approach. Write the loop in a clear and straightforward manner. Use profiling tools to determine if it's truly a bottleneck. If it is, consider using more efficient data structures or algorithms. Look into using vectorized operations, example number pi in Python, if applicable. Asterisk data structures asterisk I should use a struct, in C/C++, or a specialized data structure instead of a standard dict, in Python, because it will be much faster. Asterisk why it's tempting asterisk specialized data structures can offer significant performance improvements in certain situations. Asterisk the problem asterisk you might be sacrificing flexibility and ease of use for a marginal performance gain. The overhead of managing the specialized data structure might outweigh the benefits. You also might not be using the dict or other general-purpose data structure optimally. Asterisk better approach asterisk start with the simplest, most readable data structure that meets your needs. If performance becomes an issue, benchmark different data structures and choose the one that provides the best balance between performance and maintainability. Consider using libraries like collections in Python, which offers alternatives like default dict, counter, and dict that can be more efficient than a plain dict for specific use cases. Asterisk micro optimizations asterisk I can save a few nanoseconds by using bitwise operations instead of arithmetic operations. Asterisk why it's tempting asterisk micro optimizations target very specific, low-level performance gains. Asterisk the problem asterisk these optimizations often have a negligible impact on overall performance and can make the code significantly harder to understand. Modern compilers and interpreters are already very good at optimizing low-level operations. Asterisk better approach asterisk focus on optimizing the overall architecture and algorithms. Choose the right data structures and algorithms for the task at hand. Avoid micro-optimizations unless profiling clearly indicates that they are necessary and provide a significant benefit. Asterisk caching asterisk I should cache the results of this expensive calculation to avoid recomputing them. Asterisk why it's tempting asterisk caching can dramatically improve performance by reducing the need for repeated computations. Asterisk the problem asterisk caching adds complexity to the code. You need to manage the cache, handle cache invalidation, and deal with potential memory issues. The overhead of caching might outweigh the benefits if the calculation isn't truly expensive or if the cache hit rate is low. Asterisk better approach asterisk start without caching. Profile your code to see if the calculation is actually a bottleneck. If it is, implement caching carefully, considering the cost of memory usage and cache invalidation. Use appropriate caching strategies, example LRU, LFU, and libraries that provide caching functionality, example functools.ru_cache in Python. Tools for performance analysis, profiling. Profiling is the process of measuring the performance characteristics of your code. It allows you to identify the hot spots, the parts of the code that consume the most time and resources. Profiling helps you make informed decisions about where to focus your optimization efforts. Asterisk Python profilers asterisk Python offers built-in profiling tools like cProfile and Profile. The cProfile module is generally preferred because it's written in C and provides more accurate results with less overhead. Other profiling tools exist, such as line_profiler which provides line-by-line performance analysis. Code examples and demonstrations. Let's illustrate the dangers of premature optimization with Python examples. Example 1, a simple summation. Explanation asterisk. In the first function, sum_list_ inefficient, we prematurely assumed that creating a list and appending elements would be faster than using range. However, range is optimized for generating sequences of numbers, and summing a range directly is much more efficient than creating a large list and then summing it. The cProfile output clearly shows the difference in function call counts and execution times. Appending to a list in a loop is generally slower than directly using optimized functions. Example 2, String concatenation. Explanation asterisk. In the first function, string underscore concat underscore inefficient, we repeatedly concatenate strings using the plus equals operator. This creates a new string object in each iteration, which is very inefficient. The string.join method, used in string underscore concat underscore efficient, is much more efficient because it allocates the entire string at once and copies the individual strings into it. Example 3, sorting. Explanation asterisk. The inefficient underscore sort function uses a bubble sort algorithm, which has a time complexity of O, and caret 2. Python's built-in sort method, timsort, a hybrid merge sort/insertion sort, is significantly more efficient, with a time complexity of O, n log n. Prematurely trying to optimize a sorting algorithm without understanding the underlying complexity and leveraging built-in tools will likely lead to worse performance. Example 4, using the right data structure. Explanation. The check underscore membership underscore list function checks for an item in a list. The check underscore membership underscore set uses a set. Sets offer much faster membership checking than lists. O1, average case for sets vs O(n) for lists. If you are doing membership checks frequently, using a set becomes far more efficient. This shows using the right data structure is more important than premature optimization. Key takeaways and best practices. 1. Prioritize correctness and readability *, write code that works correctly and is easy to understand and maintain. Optimize later if necessary. 2. Measure before optimizing * use profiling tools to identify the true performance bottlenecks in your code. Don't rely on intuition or assumptions. 3. Focus on algorithms and data structures * choosing the right algorithms and data structures is often the most effective way to improve performance. 4. Use built-in functions and libraries * leverage the optimized functions and libraries provided by your programming language and framework. They are often more efficient than custom implementations. 5. Consider caching strategically * use caching to reduce the need for repeated computations, but be mindful of the complexity and overhead that caching introduces. 6. Don't optimize prematurely * resist the urge to optimize code before you have a clear understanding of its performance characteristics. Make it work, make it right, then make it fast. 7. Document your optimizations * if you do optimize your code, document the reasons for the optimizations and the performance improvements that you achieved. This will help other developers, and your future self, understand why the code is the way it is. 8. Test your optimizations * after making optimizations, be sure to thoroughly test your code to ensure that you haven't introduced any bugs. By following these guidelines, you can avoid the pitfalls of premature optimization and write code that is both efficient and maintainable. Remember, focus on delivering value first, and optimize only when it's truly necessary and based on solid evidence. Okay, let's dive into a very common error in programming, one that can be a silent killer of performance, readability, and maintainability: unnecessarily complex or premature optimization. I'll break down what it is, why it's bad, when it's tempting, and how to avoid it, using code examples across a few languages to illustrate the point. The error: unnecessary complexity / premature optimization. The error boils down to this: spending time and effort to optimize code before you know if the optimization is needed and before you have a clear understanding of where the real performance bottlenecks lie. It often manifests as * using overly complex data structures or algorithms when a simpler solution would suffice. * Writing verbose or convoluted code in the name of speed, sacrificing readability. * Focusing on micro-optimizations that provide negligible gains while introducing complexity. Asterisk optimizing code that is rarely executed or has little impact on overall performance. Why it's a problem. 1. Reduced readability and maintainability. Asterisk complex code is harder to understand, debug, and modify. When you try to optimize prematurely, you often end up with code that's difficult for others, or even your future self, to work with. Asterisk if the optimization isn't necessary or effective, you've introduced complexity for no benefit. 2. Wasted time and effort. Asterisk optimization can be time-consuming. Spending hours optimizing code that doesn't need it is a poor use of resources. Asterisk the time you spend optimizing could be better used on developing new features, fixing bugs, or improving the overall architecture of your application. 3. Increased risk of bugs. Asterisk complex code is more likely to contain bugs. Optimization often involves intricate logic, which increases the chance of introducing errors. Asterisk these bugs can be difficult to find and fix because the code is already complex. 4. Hindered evolution. Asterisk overly optimized code can be difficult to change or refactor. If you need to modify the code later, you may have to unravel complex optimizations, which can be time-consuming and error-prone. Asterisk this can make it harder to adapt your application to changing requirements. 5. False assumptions and incorrect optimizations. Asterisk premature optimization is often based on guesses or assumptions about where the performance bottlenecks are. These assumptions may be incorrect, leading to optimizations that don't actually improve performance or even make it worse. Asterisk real-world performance is influenced by many factors: hardware, operating system, other processes, so it's difficult to predict without profiling. 6. It goes against sound development principles. Asterisk make it work, make it right, make it fast. Kent Beck's principle highlights that the initial focus should be on correctness and clarity. Asterisk Yagna, you ain't gonna need it. Don't add complexity or optimization until it's demonstrably necessary. When is it tempting? Premature optimization is particularly tempting in the following situations. Asterisk when you're dealing with large datasets or computationally intensive tasks. Asterisk you might feel the urge to optimize early to prevent performance problems later. Asterisk when you're writing performance-critical code. Asterisk such as game engines, scientific simulations, or real-time systems. Asterisk when you're working with limited resources. Asterisk like embedded systems or mobile devices. Asterisk when you have previous experience with performance issues in similar projects. Asterisk you might be tempted to apply optimizations that worked in the past, even if they're not needed in the current project. Asterisk when you have a strong background in optimization techniques. Asterisk you might be eager to apply your knowledge, even if it's not necessary. How to avoid it, the correct approach. 1. Write clear, readable code first. Asterisk focus on writing code that is easy to understand, maintain, and debug. Asterisk use meaningful variable names, comments, and proper indentation. Asterisk follow coding conventions and best practices. 2. Measure, don't guess, profile your code. Asterisk use profiling tools to identify the actual performance bottlenecks in your code. Asterisk profiling tools can help you pinpoint the specific lines of code that are consuming the most time or resources. Python C profile module, Java profilers, example Visual VM, JProfiler, and JavaScript's browser developer tools are excellent examples. Asterisk measure performance before and after any optimization to ensure that it's actually having the desired effect. 3. Focus on the 80-20th rule, Pareto principle. Asterisk the Pareto principle states that roughly 80% of effects come from 20% of causes. In terms of performance, this means that a small portion of your code is likely responsible for the majority of the performance issues. Focus your optimization efforts on that critical 20%. 4. Optimize at the right level. Algorithmic optimization. Often, the biggest performance gains come from choosing the right algorithm or data structure. For example, using a hash table, dictionary, instead of a list for lookups can dramatically improve performance. Architecture/design optimization. Sometimes, the best way to improve performance is to redesign the architecture of your application. For example, using caching, asynchronous processing, or distributed computing. Code level optimization, micro-optimizations. These are the smallest scale optimizations, such as loop unrolling, inlining functions, or using bitwise operators. These optimizations are often less effective than algorithmic or architectural optimizations, and they can make your code harder to read. Typically only consider them after exhausting other avenues. 5. Keep it simple, KISS principle. The KISS, keep it simple, stupid, principle states that most systems work best if they are kept simple rather than made complicated. Avoid adding unnecessary complexity to your code in the name of optimization. 6. Test thoroughly. After making any optimizations, test your code thoroughly to ensure that it still works correctly and that you haven't introduced any bugs. Use unit tests, integration tests, and performance tests to verify the correctness and performance of your code. 7. Refactor and improve gradually. Don't try to optimize everything at once. Instead, identify the most critical performance bottlenecks and address them one at a time. Refactor your code incrementally, testing after each change to ensure that you haven't introduced any regressions. Code examples, with demonstrations of the error. Let's illustrate the premature optimization error with examples in Python, Java, and JavaScript. Python example, string concatenation. The problem concatenating strings in a loop. The premature optimization, avoid this. Why it's bad. In Python, strings are immutable. Each plus equals operation creates a new string object, copying the existing string and the new string into the new object. This is n(2) complexity, where n is the total length of the strings. This is highly inefficient. The correct approach, profile and optimize if needed, but often good enough initially. Why it's better. Join strings is optimized to build the string using a buffer. It's n complexity, where n is the total length of the strings. Much faster, especially for large numbers of strings. Demonstration, with profiling. When you run this, you'll see a significant difference in execution time. The profiler will show the plus equals operation in concatenate_strings_bad being the bottleneck. Java example, using string builder. The problem string concatenation in a loop, similar to Python. The premature optimization, avoid this focusing on tiny micro-optimizations before using string builder. For example, trying to calculate the exact size of the resulting string up front. Why it's bad. Trying to perfectly size the string builder is often unnecessary and makes the code harder to read. The default capacity of string builder is usually sufficient, and it resizes itself automatically if needed. The correct approach. Why it's better. Using string builder efficiently addresses the main performance issue, string immutability. Trying to pre-calculate the exact size might give a very slight performance boost in some cases, but it's usually not worth the added complexity. JavaScript example, looping through arrays. Asterisk the problem asterisk iterating over an array. Asterisk the premature optimization, avoid this using complex looping constructs, like reverse loops, without first profiling the simpler for loop or for each methods. Or, caching the array length when it's not changing inside the loop. Asterisk the correct approach, profile first. Asterisk why it's better, or at least not worse and easier to read. Modern JavaScript engines are highly optimized. A simple for loop is often as fast as or faster than more complex looping constructs. Caching ARR length can even optimize code in some cases. Focus on readability until you have a proven need to optimize. Key takeaways. Asterisk prioritize readability and maintainability. Asterisk write clear, concise code that is easy to understand. Asterisk measure before optimizing. Asterisk use profiling tools to identify the real performance bottlenecks. Asterisk optimize at the right level. Asterisk start with algorithmic and architectural optimizations. Asterisk keep it simple. Asterisk avoid adding unnecessary complexity. Asterisk test thoroughly. Asterisk ensure that your optimizations are effective and don't introduce bugs. Asterisk don't be afraid to refactor. Asterisk improve your code gradually, testing after each change. Asterisk remember that perfect is the enemy of good. Aim for good enough first and optimize only when necessary. A functional and understandable solution is usually better than a prematurely optimized one that's hard to work with. By following these guidelines, you can avoid the trap of premature optimization and write code that is both efficient and maintainable. Good luck.